The cryptographic mathematics protecting our daily communications are usually vetted by human experts. Recently, an AI model analyzed those secure systems and independently located hidden mathematical flaws that researchers had missed for years. This animation tracks the required resources. The model spent 60 hours working autonomously, burning through $100,000 in computing time. It weakened Hawk, a post-quantum signature scheme, and then found vulnerabilities in a stripped-down version of AES, the Internet's encryption standard. We are watching these models produce original, expert-level scientific findings. The technology has evolved from simply answering user prompts to conducting autonomous research. That cryptography discovery serves as an early indicator. We are watching a large-scale digital workforce come online across multiple industries. Workflows are shifting. Where an engineer once used AI as a tool to write code, they are now beginning to manage AI systems that execute the build themselves. At machine speed, this shift changes the requirements of professional labor, prioritizing the oversight of these digital entities over manual execution. To see this digital workforce execute complex, multi-stage projects at scale, we have to look at the software industry. Inside the AI company Anthropic, a popular developer tool known as Bun required a complete rewrite from one programming language to another. This timeline visualizes the exact velocity of that project. A small team's year-long job was finished in 11 days. That speed was achieved by 64 distinct AI agents working in parallel at a total computing cost of $165,000. When weeks of coding are compressed into hours, writing the code is no longer the primary bottleneck. Traditional corporate project management timelines simply collapse. But these massive AI swarms require specific engineering to keep them from crashing under heavy traffic. They rely on the Model Context Protocol, the communication standard that allows agents to reach out and access tools or data. Under the old version of this system, agents piled up stale copies of files in their memory. This wasted computing resources and capped how many agents could operate at once. This diagram shows how that protocol was just redesigned to be stateless. This means the servers behind the agents no longer have to store every single ongoing conversation on one machine. Flashy agent demos grab the headlines, but unglamorous infrastructure upgrades like this are what make a scalable AI workforce economically viable for a business. Powering those agents requires massive physical scale. Moonshot AI recently released Kimi K3, a model containing 2.8 trillion parameters. The underlying data for Kimi K3 is open and free to download. But the actual weight files total 1.56 terabytes, meaning you need elite data center hardware just to turn it on. Yet the consumer experience is becoming much more accessible. OpenAI recently launched a new AI coding assistant that attracted 10 million users in exactly 2 weeks. The internal adoption data reveals an interesting trend. 1 in 5 of those new users are not software developers. The technical barrier to entry for software creation has dropped significantly. People with no programming background are now assembling functional software for their own office workflows. While data center models grow larger, researchers are simultaneously mapping the exact mathematical limits of how far these systems can be compressed. Liquid AI recently introduced new text processing models, engineered to run directly on standard computer processors, bypassing the need for expensive graphics chips. This chart plots the resulting processing time. The model can read and route an 8,000-word document with almost zero delay, running on the plain processor you already have in your laptop. This localized efficiency allows companies to run powerful AI on their own secure internal hardware, keeping sensitive data entirely out of the cloud. Putting autonomous capabilities on local networks introduces immediate risks. A recent benchmark test called AlloBench measured how well these models handle actual resources. The frontier models tested perfectly when asked to describe a budget in plain text, but when trusted to execute actual code and spend real resources, they frequently broke down. That blind spot escalates quickly in the real world. Security researchers recently observed an AI agent autonomously chaining together a series of unknown software flaws to execute a continuous 5-day cyber attack. Machine speed offense often outpaces human defense. When automated systems can probe networks 24 hours a day, everyday vulnerabilities become much more expensive to secure. The AI can rewrite legacy code and locate hidden flaws, but it is blind to whether its own output is actually true. Because of that, scientific and development teams now spend the vast majority of their working hours testing, fixing, and verifying what the AI generated. Technical execution is rapidly becoming a commodity. As the cost of building complex systems drops, human taste and judgment become the primary scarce resources. In an environment where code and research can be generated at scale, the human role centers on discernment. The value lies in deciding what is actually worth the resources to build.